Great. So now we'll move on from neural networks to social networks. And Ana-Andreea Stoica will tell us about algorithm design for social networks, focusing on diversity and inequality.
Great, thank you. Thank you everyone for being here. I'm Anna. I just finished my PhD at Columbia in computer science, and I'm going to start my postdoc in Germany, in Tubingen, just after this program. So I'm excited to talk to you about a brief overview of my work on algorithmic design for social networks. In my work, generally, I focus on thinking about questions of diversity and inequality. And the main questions that I've been working on so far is how do you diagnose and mitigate algorithmic bias to create fair, efficient, and useful algorithms? Thinking about how different algorithms may affect different subpopulation in your graphs, in your networks. For the first part, I've worked on mostly recommendation systems and ranking systems regarding search, for example. And for the second part of the question, I've worked on redesigning algorithms for cases like information diffusion or clustering. So I want to start with a small example of what does it mean to even think about algorithmic bias, how would it affect different communities in the context of networks. And I want to start with this data set that was collected by our lab, by our collaborator, Chris Reeder, a few years ago. It's a very interesting data set, and I know we've had a short discussion about having a data set session. This is something, if you're interested in, I'd love to share it with you. It may be useful for many applications. This is a graph data set with people as nodes, as users on Instagram, and edges whenever they link, they like or comment on each other's photos. And there's two main groups that we have in this data set, men and women in different proportions. And the interesting part is that they only have these organic connections to each other. So this data set was collected before the who to follow feature was implemented on Instagram. So there's not a recommendation feature to it. It's just however people connected naturally to each other. There's many other features like timestamp location, hashtags for which you can do a topic analysis and so on. The first thing that we looked at was to say, well, how many connections do people have? What is the degree distribution and how does that differ between the two communities? And first of all, it's kind of like a power law degree distribution in general, but more than that, here I'm showing in blue for the original graphic, nor the other colors, the percentage of one of the group, in this case, the women, among those with degree at least X. So as the degree increases, the percentage of one of the group among those with degree at least X goes to 0, showing that one of the groups is like essentially not represented at the very top of the network with people with very popular degrees. And you may think that's not a big deal. That's just like how the data looks like. Of course, it's not something that we introduce in the data. But what we did here was to say, well, what happens when you have recommendations that are based on friends of friends? For example, looking at recommending people based on the atomic odor index or a random walk of length 2. And if you look again at the percentage of one of the group among those with degree at least x-axis, in green and in red, you see that the percentage of one of the groups, in this case, the women, drops to 0, but much faster. So there's this gap that got amplified in a way. And this is an example of what I mean by this amplification of inequality between the two groups. And in this case, we looked at the degree because that's a measure of social capital that was mentioned heavily last week as well. And it may matter in your ability to form new connections in the future, whether they're algorithmic or organic. One way to explain this was to look at graph models, and we're able to explain this kind of phenomenon using preferential attachment and homophily in a model that also embeds recommendation. And in doing so, what we notice is that, well, we know preferential attachment has a power law degree distribution. People have shown that if you have two communities and they're kind of homophilic, you have a power law degree distribution, but with two different coefficients. And if you do these recommendations based on friends of friends, that difference between coefficients would actually increase. And that's the kind of inequality that you see being amplified or perpetuated at the level of recommendations in this data set and several other data sets. So there's a lot of theoretical, interesting questions that come from this kind of analysis and models that don't relate only to the percentages of different people among people with high degrees, but tell us exactly what are the mechanisms that create this kind of effects. And homophily was a big one here. It's a necessary condition to get this kind of difference. There was a question yesterday at Nicole's talk as well regarding what happens if you have differential homophily. And that's another very interesting, also theoretical question that we looked at in the context of recommendation and ranking also actually. And you get a very interesting effect where one of the group is more homophilic. You can actually reverse this kind of effects here. And you're able to get a better degree distribution, or basically a group gets way higher degrees. So a bit short on that. What do we do with this kind of information? I want to argue for a very quick overview of our recent work was that this kind of community level information and analysis was really helpful to think about, well, how do you restore this kind of like lost lost parity on who gets to have a high degree or a high number of connections in this case. And we did that in the context of information diffusion in the social influence maximization problem that we talked about last week in the boot camp, where the point is to choose a number of people from which you see the information to in the network and rely on them to spread it to the network. So we have to choose these. The choice of these early adopters is the optimization problem that we care about. And generally, we can do that by just having some approximation algorithms based on centrality or greedy. However, these they're pretty agnostic to communities. They do pretty well in practice, but one recent concern is that people have shown that, well, if you have different communities, the kind of bias that you see in the degree distribution will be also perpetuated at other kind of centralities, and you end up with one of the groups being left out of the information loop. And that's a kind of issue where we're thinking about solving and using the information that I showed you before. So in doing that, we can think about adding back this lost parity between the two groups here, red and blue, as a constraint. And if we add it as a constraint in the outreach of our optimization function, you end up with a solution that gets you a trade-off between being fair and being efficient. It doesn't reach as many people as you would otherwise if you don't think about communities at all. What we're doing with this kind of network models and results that I showed you before is that, well, you can actually overcome that. And if you add it as a constraint at the early adopter set, and using the kind of network models, particularly homophily is an important part of this, you can use this to estimate the size of your campaign and to show that there are many conditions in which being fair, being diverse can actually help you being more efficient in optimizing your outreach. It gets you many more people than before. This is, I guess, conceptually related to what also Nicole was talking about yesterday in the case of the labor markets. When you add more diversity in your referrals, you're able to get more people active into the labor market. And if you don't, you end up with fewer people because the people who are in a majority group or advantage group will just recommend each other or recommend the same people. So how would that look like? Well, the key parameter here is to look at the size of the seed set. And the different parameters we have here, whether it's like how big is the minority, how homophilic is the network. This is just one example of particular network models generated from preferential attachment with homophily, is to show that, well, agnostic meaning that you don't look at communities. In that case, in this kind of case, set of parameters, you would do better by being agnostic using centrality metrics or a greedy algorithm than being fair. Being fair, I'm just using diversity and parity as two different heuristics that we were using to satisfy the constraint that I showed you before. And when you get to a high enough number of seeds, that's where being fair, either through diversity or parity, will get you a better outreach. So these colors basically represent you who gets you the better outreach, when are you able to be more efficient. And that's very related to the work of Amin Saberi, who was talking about it last week, just a few seeds more, in which they show that, well, if you add just a few more seeds in your information diffusion case, but randomly, you're able to reach more people overall than you would otherwise by optimizing the problem itself. And the reason for that is that, well, you're getting to parts of the network that you wouldn't get otherwise. And in this case, by adding more diversity constraints, you're getting to a part of the network that actually has lower centrality, but you actually didn't reach it overall very well. And this doesn't happen just with centrality metrics, happens with greedy algorithms too. But it's much easier to show it in theory for centrality metrics. So I want to end here and just discuss very quickly open directions, because I think some of them we've discussed, and maybe some of them will be topics of the reading groups. And I'm happy to talk about any of this. Some of them I've started to think about, but some of them I have not. The first one being generalizing beyond particular parametric network models and thinking about what specific properties can cause this kind of difference between groups to be projected onto different embeddings. A particular application of that is that on ranking that I'm currently working on, and thinking about, for example, PageRank uses particular spectral embeddings of the network data to do so, and how does that reflect on different communities? Second, how can we figure out that it's a particular algorithm that causes bias or it's something else happening? The reason this Instagram data was particularly helpful was because it was a graph devoid of any recommendation. It was collected before any recommender systems were implemented. So we can see whenever you simulate one, you can see what's the effect of that particular recommendation algorithm. It would be great to get this data after recommendation algorithms were actually implemented. It was much harder to get it later on after they were actually implemented, but it's nevertheless interesting to look at. Also looking at feedback loops and long-term effects, thinking about how do we, what does happen as the network evolves. A lot of this analysis that I've shown you and a lot of the proofs are based on on a model of network evolution that relates to methods we've talked about last week as well. I'm also interested in how do people evolve jointly with a particular algorithm, and I know people here work on that, particularly Hara and Nika as well. How do we think about multiple objectives and fairness beyond the being a constraint? Sometimes adding it as a constraint leads to these trade-offs, but sometimes, as we saw here, it doesn't have to do that. And generally thinking about interdisciplinary stuff that I don't have to talk about as we all come from different backgrounds here. But I'll end here. I think we're on time. So thank you. I can take questions now.
Thank you very much. Wonderful talk. I have a question on your very first thing where you started with the degrees and then looked at something like PageRank or other recommendation algorithms, which sort of look out for further in the network. Mm-hmm. And you are arguing that this means that the algorithm is amplifying bias. But I wonder whether, I mean, if I just took that as a social network, I have no algorithm and people do recommendations, they act sort of by, you don't just look at the degrees, right? You may sort of look at people with high degrees, but then you look what kinds of friends they have and are their friends influential. And people like Duncan Watts studied, if you look how sort of viral tweet spreader. So it's actually not the first node which matters with this high degree, but actually the nodes, the degrees further down. Yeah. So one could argue that actually these other measures just tell you that your social network is even more biased than you thought, and your algorithm just teases it out. And if you only look at degrees, you don't even realize how biased your social society is.
Yeah, that's a good point. That's something that's like hidden in the average, by the way. If you look at average degree, you would never see this kind of difference in effects, but you would see it when you look at the tail. And the tail, I'm guessing you're saying that it's something that will create this amplification or will show this amplification in the case of recommendation. What happens actually is you end up with more polarized groups. And it's not that in itself that they're more polarized, but it's the fact that the people who have very high degree are entering this rich get richer effect that gets even more amplified. Yeah, good question.
Anyone else? Question? Okay, thanks. Lovely talk.